With these algebraic results in place, we are now ready to come to some key conclusions. Notice that if we apply this L plus or minus operator to y lambda m, what we've just found is that what we get back is a pure state with respect to both L squared and with respect to LZ. But the YLMs, or these Y lambda M's, are by their very definition those pure states. They are what we call those corresponding pure states. Therefore, this L plus minus Y lambda M must be equal to the pure state, which we've called Y, that has a lambda value lambda, but it must be the pure state, of course, with M, a different pure state. It's either with M with a plus 1 or a minus 1. But we know that that's what this must be because this function, we've just proved, satisfies the very criteria for being precisely this state. Now, there is one little proviso, of course, which is that all of these are linear equations. So this state has the right pure state values. We just can't be sure whether or not it's properly normalized. So there may be some normalization constant that comes in. So B would be some arbitrary normalization constant. And you can actually work out what the value of that constant is in much the same way you do with the harmonic oscillator. So that's one of our very key points. Now, the second point has to do with the limitations on this, because you may also recall that there are bounds on M, right? M, its absolute value, has to be less than or equal to lambda. Now, we don't know if M actually could ever reach or equal to lambda, but its absolute value is bounded by lambda because M is the z component of the angular momentum, which in magnitude has to be less than the total magnitude of the angular momentum. And the other thing that we know about M is that M has to be an integer value. Now, you might ask yourself, well, what happens actually if I take the last possible maximum value of M and then try to apply my L plus operator to that particular state? So let's write down mathematically, precisely what I'm talking about here. Now, because of these constraints that I've just mentioned, we can define then L, a new integer L, which is going to depend, of course, on which total angular momentum sequence of states I'm talking about. And we're going to define that as the maximum allowable value of M. We know there is some maximum value allowed for M for a given lambda because M can't exceed a certain value, and M is an integer. So we know there is a certain maximum value. And then we can ask what will happen if I apply L plus to that state, to that Y lambda L state, where L, remember, is just this maximal possible value of M. I could write it as M sub max, just as a shorthand to remind myself what I'm doing. Well, by this very algebra that we've carried through, if this gives me a valid state back again, it will necessarily have a higher value of M, and that leads me to a contradiction. The only way out of that contradiction is if what this gives me back is in fact 0. This is the terminating state for the maximum value of M for this particular situation. Now, given this, then, what we have are two things that we can do with this. The first very nice thing is this gives us a linear, because the L operators are linear, right? They're at linear order. It gives me a linear operator equation for, then, this maximal state, Y lambda L. And you can actually solve this without too much difficulty, and then that can give us, you can solve, and then you can get an expression for Y lambda L. And then, of course, once you know Y lambda L for the maximum value of M, you can then get the remaining Y lambda M's for that value of lambda by applying L minus to various powers, L minus, say, to the nth power. So this gives us a very quick way to generate all of these spherical harmonic functions. Very nice. Now, this equation has one other very important consequence, in that it tells us what the actual allowed values of L squared are. And that comes back to the very beginning identity that we were looking at in this lecture. So the final note I'd like to observe, the final piece of algebra, final bit of algebra, is that I can use the properties of this terminating state to compute the possible values of L squared. So if I apply L squared to y lambda L, this maximal state, I actually have two ways to compute this. The first way is simply to recognize that, well, by very definition, this is a pure state of L squared, and its pure state value is lambda squared h bar squared. The second way is to realize that L squared has an expansion in terms of my fundamental L plus minus operators. And that expansion actually is L minus, there are two versions of it. This will be the more useful version. If you want to be reminded, we had it way up here. It's the product of the L's, and in the upper order, minus plus, it comes with a plus h bar LZ. The lower order, L plus L minus, comes with a minus h bar LZ, and they of course all have LZ squareds in them. So I'm going to focus on this particular order for reasons that you will see in a moment, plus then h bar LZ plus LZ squared, all applied to y lambda L. Now I can evaluate this using the known properties of my operators. And the key observation is that when I'm talking about the terminating state, when I apply L plus to that state, by its very defining relation, I get 0 for this first term. So the first term is going to give me back 0. The next term will give me h bar times the result of applying LZ on y lambda L, but the result of LZ is just m times h bar, but remember L is my particular value of m. It just happens to be my maximum value. So LZ applied on y lambda L, will give me an h bar times L back again. So that's h bar squared times m, and it gives me times my state back, of course. And then when I apply LZ to this state, this is the m at this point is the maximal value, which is L. That's the particular value of m I'm looking at. When I apply LZ to this the first time, it gives me h bar L. And when I apply it times my state, and when I apply it the second time, I get another factor of h bar L. So it's a net h bar squared L squared multiplying my original state back again. Now from here, because the y lambda L is not all 0 everywhere, I can equate the prefactors to each other. And moreover, you will notice that dimensionally the equation is correct and it has h bar squareds everywhere, so I can cancel all of these h bar squareds. And what I learn then is that the value of lambda squared, this actual magnitude of the angular momentum, turns out to be very closely related to L. It's not exactly L squared. It's L squared plus L, which is L times L plus 1. And that is one of our key conclusions, because that tells me then what the allowed values of L squared are, right? The constant A that we've been seeking, right, that allows us to now shift our attention, right? This A is just the allowed eigenvalues of L squared. I can now take this A constant and set it equal to the radial parts of my equation, and I can then continue my analysis to determine all of the allowed energies for the atom. So this is going quite well. So we now have this one key result where I can determine what lambda squared is, where then, remember, the constant A I'm looking for is just lambda squared h bar squared. The allowed values for lambda, this is the key point, are these L's times L plus 1. Now, L itself, notice, must be an integer because L is actually equal to the maximum possible value of m for a given lambda, but the m's themselves are integers, so therefore the L's must be integers. And they turn out to be not just any integers. L is the maximum value of an allowed m for a given lambda. And this is a little bit of a subtle argument, but I'll give it to you very quickly. L cannot be a negative integer. The maximum value of m cannot be negative. And the basic reason for this is if we think about what m represents, excuse me, it represents the angular momentum or rotational motion, right, of the system about the z-axis. And if I had any state that had a negative value of m, right, that would represent rotation going backwards around the axis. By this famous time reversal symmetry that our equations obey, basically just taking the complex conjugate of that function, because my del squared operator is all a real operator, because L squared was all written in terms of real variables, I know if I have a solution, I can always take the complex conjugate of that solution and have yet another valid solution. And if I had a backward traveling state with an e to the I, say, m phi, traveling with backward angular momentum, by complex conjugating this state and generating the time reversed version of that negative m state, that version, its complex conjugate, would come out with a positive value of m. So therefore, if there are any values of m for a given lambda, if the maximum one were negative, I get into a contradiction because I can know from any of the negative ones I can generate positive values. So I know there are positive values for m, or at least not negative values. The one exception is, well, if m is 0, then I'm just stuck at 0. So the conclusion of this then is that L could be 0, of course. L cannot be, though, a negative number, because that would imply the existence of positive m values for states by this time reversal or complex conjugate argument, and so therefore L must be a non-negative integer. So L then would have to equal 0, 1, 2, etc. And that then really wraps up our discussion, because we now know the allowed values for lambda squared from the formula that you see here. We also, by the way, know the allowed values for m, because m, notice, has its maximum value as L. It certainly could have 0 values. I can get that by applying my lowering operator. And then I have a whole sequence of states. The lowest possible state, by that time reversal argument, would actually have to be the minus of the top state. So m varies from minus L up to 0. And that's our key central conclusion.